Hi there, this is Callan Bentley. Welcome back for a pre-lab video. This week in lab we're going to be taking a look at some rocks. We're going to be thinking about the rock cycle, which is how one kind of rock can turn into another kind of rock. And we're going to identify rocks with the aim of interpreting the conditions under which they formed. This is a diagram in your lab manual describing the rock cycle. You can see that there are sort of 5 major points here on this rock cycle, and there are all kinds of arrows leading from these different hubs towards one another. So first off, let's start with molten rock in the upper left corner. If molten rock is underground, we call it magma. If it's above ground, we call it lava. Regardless, that molten rock can cool and crystallize, and when it cools and crystallizes, it makes igneous rock. So the upper right corner of our diagram shows igneous rock. If igneous rock forms above the surface of the Earth, we call it extrusive igneous rock. And if it forms below the surface of the Earth, we call it intrusive igneous rock. Now, those igneous rocks can be weathered and broken down to produce sediments. So weathering produces sediment. That sediment is then transported away from its origin and ends up somewhere else where it's deposited. And then that sediment gets stuck together through the processes of lithification. It can get compacted or squeezed tighter, or new mineral cements can basically stick the individual grains of sediment together. This makes sedimentary rock. That sedimentary rock might be exposed to excessive heat or pressure, and that can cause it to metamorphose. If you metamorphose sedimentary rock, you end up with metamorphic rock. And of course, if you take that metamorphic rock and you heat it up even more, you can end up melting it, forming magma. All right, so now we've come full circle here on our rock cycle diagram. You'll note that there's also some blue arrows in the middle, and those blue arrows basically can lead us from any of these other rocks to different points on the rock cycle. So, for instance, we could go from intrusive igneous rock and melt the rock and make magma again to make more igneous rock, or we could metamorphose that intrusive igneous rock. We could take a metamorphic rock and weather it to produce sediment. We could take a sedimentary rock and weather it to produce sediment. We could take a metamorphic rock and metamorphose it. So those are all valid possibilities as well. To identify igneous rocks, you're basically going to be paying attention to 2 things. One is the composition of the igneous rock, and then the second thing is the texture of the igneous rock. Basically, a combination of the texture and the mineral composition will give you the igneous rock name. For instance, if the rock is mostly dark, that gives us something in this column. All right, it's a mafic composition, and if it's fine-grained, that gives us something in this row. The intersection of that column and that row is one rock and one rock only. That's a basalt. So a basalt is fine-grained and mafic. A granite, on the other hand, would be coarse-grained and felsic in composition. And you can see the other textures such as porphyritic, glassy, vesicular, and pyroclastic. They can have various compositions as well. With sedimentary rocks, basically you're going to take a look at a couple of things right off the bat, and then if those don't work, then you're going to default to some other possibilities. First off, you want to look to see if you can make out particles. If a sedimentary rock is made out of chunks of other rocks, that makes it a detrital sedimentary rock. It can be made out of big chunks, gravel. It can be made out of medium-sized chunks called sand, or it can be made out of very small chunks, which we call silt or clay or mud. If the sedimentary rock fizzes when you put hydrochloric acid on it, that indicates that calcite is one of the major minerals in that rock, and therefore it's going to be some variety of limestone. All right, and you can see there's various kinds of limestone depending on the different distinctive properties. So if your rock doesn't fit one of those 2 categories, if it's not detrital or limestone, then it might be one of these other possibilities down here. We could have really fine-grained quartz, which is going to be so fine-grained you can't see the individual grains, but it'll scratch glass, so it's nice and hard, and it may have a conchoidal fracture. Depending on the color, that gets one of several different names. It could be gypsum, in which case you can scratch it with your fingernail. Halite would taste salty. And altered plant fragments make coal. That coal is going to be distinctive because it's black and it's brittle. Okay, with metamorphic rocks, the essential breakdown is going to be foliated or non-foliated. Examples of foliated metamorphic rocks are shown up here on the top. That's where there's an alignment of the mineral grains within it. Marble and quartzite, anthracite coal, hornfels, those are all nice examples of non-foliated metamorphic rocks. Metaconglomerate can be either foliated or non-foliated, and serpentinite is probably best classified as non-foliated as well. Here it's going to be a little bit less systematic. The first thing you should look for is whether there's foliation or not, whether there's an alignment of the mineral grains, but then those distinctive properties are going to be critical for identifying the individual metamorphic rocks. Let's go to my students now and take a look at a couple of examples.
Here we have a primary sedimentary structure, mud cracks. We can tell two things from this. We can tell because of the cracking that it was exposed to the air. If it was underwater, it could not have dried out. And the red color indicates that it was in an oxygen-rich environment.
So here we have two non-foliated metamorphic rocks, marble and quartzite. Now they're both very similar. They both have a sugary texture. The only way we can really tell the difference is with acid. The marble, which is made out of calcite, should fizz. The quartzite, which is made out of quartz, should not.
Here we have a granite rock, which is igneous and it's formed from magma that was underground and it was cooled and uplifted, and it can be weathered away and create sediments like this gravel here.
The sediment can then be transported and lithified later and made into a conglomerate like this, which is a sedimentary rock. And then it can later be under pressure or heat and made into a metamorphic rock like this metaconglomerate.
Okay, so summing up here, you can see three different outcrops here, and these three different outcrops are made out of three different kinds of rock, which tell three different stories. The example up at the top shows a bunch of basalt. That basalt is vesicular, meaning it has gas bubble holes in it, and that tells us a story of ancient lava eruptions. So there was a volcano that erupted there at that site in the distant past. The image in the middle shows a cross-bedded sandstone, and that sandstone, based on those big crossbeds, that must be the signature of an ancient sand dune. Lastly, down at the bottom, we see the kind of rock that we'd find deep at the bottom of the Grand Canyon. That's a schist. And that schist, as I mentioned in the introduction, is indicative of ancient mountain building processes. So when we see a schist, we should imagine the roots of ancient mountain ranges. It's funny to imagine that the Grand Canyon, which is a big hole in the ground, actually used to be at the roots of ancient mountains, but that's indeed what that schist is telling us. Hopefully all this makes sense to you. Thanks a lot for your attention. I hope you have a great time in lab this week identifying these different rocks. This has been another pre-lab video.